Hello, and welcome to Lecture 3 of the Forces unit of Physics 1101. And we're working towards Newton's second law. We saw this statement that forces cause accelerations, and we're going to work that into Newton's second law more precisely. But it's actually going to take us 2 lectures to get there. Our starting point in this lecture is to think about what mass is. So mass is most often defined as the amount of matter in an object. And if you find that definition kind of vague, you're on to something, because mass actually is pretty problematic. And the more physics you learn, the more you realize that mass is kind of a hard concept. We compare 2 masses using a balance, like this very old-fashioned brass balance here. And so you can measure a mass by comparing it with known masses. So here's a triple arm balance that you would use to do that. This is often referred to as a balance, this electronic device, but it's not really a balance, it's a scale, and we'll see why and what the difference is in a moment. But you might see that there's a bit of a problem here. How do you start this process if all measurements of masses involve comparing with known masses? How is the first mass measurement done? Well, remember back to measurement, that all measurements are comparisons. So before you can do any measurement of anything, you need to set a standard. And so the standard currently is this chunk of platinum that's stored in Paris. And originally it was based on a known volume of water. A kilogram was defined as the mass of a liter of water. One of the reasons people are often confused by mass is that they mix it up with weight. Mass is quite different from weight. While mass is the amount of matter in an object, weight is a force. It's the force exerted by gravity on the object. So you measure mass by comparing with other masses, like on a balance, whereas you measure weight by comparing with other forces, such as a spring scale. So that thing on the previous page that I said was not a balance isn't a balance because it's comparing the force down on it by the thing you're weighing with either the compression of a spring or maybe a more advanced electronic thing like a strain gauge. Mass is the same no matter where you measure it, but the weight changes if you measure it in a different location. So for example, if you measure the mass of an object on Earth and take it to the moon and measure it again, it'll be the same there, but you'll find that its weight is smaller on the moon than it is on Earth. But part of the reason for the confusion is probably that weight and mass are closely related to each other. It turns out that weight is proportional to mass, so we calculate a weight, W, from a mass by mg. We should discuss what proportional means. If you're aware of politics, you will have heard of this idea of proportional representation. And it simply means that you take the percentage of the popular vote and you assign each party a number of seats in Parliament proportional to its percentage of the popular vote. If they get 40% of the popular vote, they get 40% of the seats. Now, it might not seem all that relevant to physics to be talking about the politics of proportional representation, but it's the same idea as the sort of relationship between weight and mass. Here is what we call a proportional relationship. So we have some variable y, I don't know what it is, and it's related to x, some variable x, by this relationship, where a is some constant. And so now if x changes by some factor in this relationship, then y changes proportionally. In other words, it changes by the same factor. So if you double x, y will double. If you divide x by 3, y will also be divided by 3. So this is the real meaning of proportional. And on a graph, it gives you a linear relationship with an intercept of 0. So this equation, y equals ax, is saying that if you put y on your vertical axis and x on your horizontal axis, then you will get a straight line with a slope of a. And so now we see that this relationship between weight and mass is a proportionality relationship. The weight is related to the mass by a straight line relationship with slope g. And this g is the g we've met, acceleration due to gravity, so on Earth approximately 9.81 meters per second squared. But remember that it varies from place to place, and that's why, even though mass is the same everywhere, weight isn't, because, for example, on Earth g is 9.81 meters per second squared, and so that gives you the slope of this relationship, but on the Moon it's only about 1.63 meters per second squared. We can talk about units now. Remember that this weight is a force. And so this equation is all we need to figure out what units of force are. So I can say that a force, using this equation, is clearly a mass is in kilograms, and I multiply that by g, which is an acceleration in meters per second squared. And so those are the units of force, kilogram meters per second squared. But that's kind of a mouthful, isn't it? So we define the Newton, right? We call it N. And 1 Newton is 1 kilogram meter per second squared. So here's an easy experiment, sort of easy. You take a mass, let's say it's a kilogram, and you exert a 2 Newton force on it. Now the hard part of the experiment is making sure that this is the only force that matters, right? So you need to make sure you don't have to worry about friction and things like that. So maybe you do this with an air puck. What you find is that the acceleration of this object turns out to be 2 meters per second squared. Now, you repeat the experiment with exactly the same object, so you've kept the mass the same, but now you exert a 4 Newton force on it. And what you find when you carry this experiment out is that it'll accelerate at 4 meters per second squared. So what this is showing is that the acceleration of an object is proportional to the force on it. Same meaning of proportional that we were talking about earlier. And this perhaps doesn't surprise you. If you pull twice as hard on something, it will accelerate at twice the rate. So now you can do a very similar experiment. You take your mass of 1 kilogram and you exert a 2 Newton force again on it, being careful that that's the only force that matters. And now, instead of changing the force, you change the mass. So you replace your 2 kilogram object, or your 1 kilogram object, with a 2 kilogram object. And what you now find is, well, the acceleration of this one we already know. It's 2 meters per second squared. When you double the mass, the acceleration is chopped in half. So more massive objects subject to the same force accelerate more slowly. You can see this yourself sitting at your desk. Now, it's hard to do this experiment sitting at your desk because friction is a problem. So one solution is to do the experiment vertically so that you won't have to worry about something sliding over a surface. You can see this yourself at home. Just take an elastic band and hang a bunch of stuff from it as I have here. And now pull it down and release it. And it'll accelerate up towards your hand. Now, remove some of the mass and try it again, and it'll accelerate up towards your hand much faster. So the experiment you just did shows that when you decrease the mass, if you keep the force the same, the acceleration increases. Now, it takes a more careful experiment to show that the acceleration is inversely proportional to the mass. Well, what does inversely proportional mean? It means that when you increase the mass by some factor, then this leads to a decrease in the acceleration by the same factor. So in other words, if you double the mass, then that means the acceleration is divided by 2. If you divide the mass by 3, then you triple the acceleration. And the mathematical relationship that gives you this, if you have any two variables, y and x, and they're inversely proportional, then the relationship looks like this. And so this tells us that our acceleration must be something or other divided by the mass. So now that we know all of the proportionalities, we can write our relationship, although there's still a detail we need. We can write that the acceleration is proportional to the force and inversely proportional to the mass. And note, it's experiment that tells us this. Maybe there's another universe somewhere where the laws of physics there say that the acceleration is a force divided by a mass squared. Or maybe the acceleration is a force cubed over a square root of a mass, right? But not in our universe. Experiment shows this. So let's do a quick example. Here we have a skater. The skater is 60 kilograms, and they're holding on to this rope. There's a 210 Newton force being exerted on them by this rope. I don't know, maybe there's another skater at the other end pulling, or maybe it's a snowmobile, which I really don't suggest. But anyway, let's find out what the acceleration of this skater is. So the acceleration is just going to be that force over their mass. And so that is just 210 newtons over 60 kilograms. And so notice that is 210 over 60. That's 3.5. And let's just check. Newtons per kilogram. That's kilogram meters per second squared. That's a newton divided by kilograms. The kilograms take each other out, and we're left with meters per second squared, as we should. Notice, if you had a heavier skater, a more massive skater, then their acceleration would be lower. If you pull harder, then this number is going to come out bigger. There are two objections that I hope you all have to what I've been doing in this lecture. The first is that I've been dealing entirely with situations where, as I've put it, there's only one force that matters. But we can't do that. We have to be able to deal with situations where there are multiple forces acting and we can't ignore any of them. But the second thing is that I've been only thinking about magnitudes of forces and magnitudes of accelerations. But as we already know, forces are vectors, and so are accelerations. And so we can't ignore that these have directionality. So that's what we'll do next lecture, and it's going to lead us to our final form for Newton's second law, which is going to look like this.